Okay, so last time we talked about resistors and resistance and what to do when we have resistors in series and parallel and how we can combine them when we have networks. So today we really want to look at the first equation that you will see in electrical engineering, and that is Ohm's law. It is the linear relationship between voltage, current, and resistance, where V is your voltage in the units of volts, I is your current in the units of amps, and R is your resistance in the unit of ohms. We can turn that into a graphical image where we have a voltage source V, we have a resistor R, and we have current. The convention that we follow is that electrical current comes through the positive side of the battery and it returns to the negative side of the battery. And it will take any path as long as, any and every path as long as it has a return path back. So we can look at two examples. The first one being a battery with two resistors in series. As we just said, the current will take every return path back, but we only have one return path back, which really says that the current going through the first resistor will be equal to the current going through the second resistor. So we can express this circuit by combining those two resistors. And we can say that the current is equal to the voltage over the resistance, which is equal to 5 volts over 5 ohms, or 1 amp. Now with the second circuit, well, we have current that will come out of the positive side of the battery. We'll go through this left-hand side 2 ohm resistor, and then it will also go through this right-hand side 2 ohm resistor. So we can't make a total I for the whole circuit right now, but we can make an I that represents current going from the battery to everything. So we know how to express this one in terms of one resistor, where these 2 ohms in parallel will be equal to 1 ohm. Then we will have 5 volts, and our current will be equal to 5 volts over 1 ohm, which is equal to 5 amps. So the battery is supplying 5 amps to the entire circuit. We don't know right now how much current is going through each branch, but we will slowly get there. So given what we have in the last video, we can have something similar where we can have resistors in parallel and series, and then series again, just this entire resistor network. And what we can do, we can simplify that whole thing in terms of one resistor, RT. Again, we will have our current going in this direction. And we can say that the current going from the battery is equal to V over RT. We don't know what the voltage at any of these nodes or what the current in each branch is. But to examine that, we will investigate something called Kirchhoff's voltage law, also known as KVL. So what KVL says is for a closed loop circuit, there is conservation of voltage. What that means is if we start at this point A, whether we go around clockwise or counterclockwise, when we get back to A, we should be at the same voltage. So if we start at A and go clockwise, what we will be saying is V A to B plus V B to C plus V C to D plus V D to A is equal to 0, and that's our conservation, where we can make the side note up here that VI to J is equal to VJ minus VI. So if we call point A 0 volts, we know that point B will just be V. If we look at for B to C, we know that we have the same voltage, and B and C are pretty much the same node, so this term will be 0. Similarly, with A and D, we have the same thing for the same argument, so that is 0, and we are just left with VD. So we can say that VCD is equal to minus V. Well, we know what minus V is, based off of Ohm's law that we just learned, which is equal to I times R. So now we have VCD is equal to minus I times R. We can plug that back into this equation up here to say V minus IR is equal to 0, or V equals IR, which is our Ohm's law. Now we have this minus sign here. What does this really tell us? Well, it shows us that we have a voltage drop over this resistance here. Because the only way, if we have some positive voltage here, is to drop down again in voltage so that we can actually get to 0 and have that conservation. So the takeaway is, when we have a circuit like this, or something similar to this, we would have voltage drops over all of the resistors. So we can go back to the previous example. We would have a voltage drop over R1, voltage drop over R2, voltage drop over R3, voltage drop over R4, and a voltage drop over R5, because our current would be going that way. So now we can investigate, or we actually want to see what the voltage is when we have more than one resistor. So we can go around this loop here. Again, we have resistors in series, and this is the only path for current to take to get back to the other end of the battery. So what we can say is voltage is equal to voltage minus I times R1 minus I times R2 is equal to 0. Now, we can call this term the voltage over R1, and this term the voltage over R2. So if we want to know what the voltage over R2 is, which is denoted by this green dot here, well, we can rearrange this equation to say VR2 is equal to V minus VR1. So, the question is, what is V? What is VR1? Can we express it in anything we know? Well, let's look at the circuit. We know that we would have something that looks like this, where RT is equal to R1 plus R2. So we can say I is equal to V over R1 plus R2. And we're going to use that because we know that VR1 is equal to I times R1. So now we can say VR2 is equal to V minus V times R1 plus R2. And then we'll have times R1. We can bring this term over to this term to have VR2 equal to VR1 plus VR2 minus VR1. This is not a subscript, this should be separate variables, over R1 plus R2. And we see that these terms will cancel out. So what we end up with is VR2 is equal to VR2 over R1 plus R2. And this is our voltage divider. So this voltage right here is equal to the initial voltage that we know times R2, which we would know, and that is divided by R1, which we know, plus R2. So that gives us our voltage divider. Now, we can look at why we would need the voltage divider. Well, let's say we have a 12 volt battery. This can be something like a car battery or motorcycle battery or some kind of voltage source or battery. And let's say we have a device that you will plug in that can only run off 5 volts. If you apply 12 volts to it, you will blow up the device. It will not work, it will break, and the warranty that you bought it with will not cover that. So we are out of luck, unless we can use something that can get us 5 volts to the input. Well, as we just saw, if we tie this node right to our input of our device, we call this R1, R2, well, we know that V in would be VR2, and we know that VR2 is equal to 12 volts over R1 plus R2, and that is times R2. So now we can set up R1 and R2 such that VR2 does not exceed 5 volts. And this will keep our device safe as long as our source remains at 12 volts. So I think we can call it here. Next time we will talk about more examples, and we will go into Kirchhoff's current law.